guys, today I'm going to present the examples of problems in working stress method. So please kindly subscribe to Civilly Learn for more videos. Let us see the first example. This is the section of rectangular cross section having a width of 250 mm and the total depth of 500 mm, and the effective cover of this section is 50 mm. Actually, there are two types of covers. One is effective cover and another one is clear cover. Here, the effective cover is given. Effective cover means from center of the reinforcement bar to the bottom of the beam. That particular distance is called effective cover. Clear cover means from the bottom of the bar to the bottom of the beam. So, in this problem, the width of the beam is 250 mm, capital D is, that is, overall depth is 500 mm, and effective depth small d is equal to 500 minus 50 mm, that is 450 mm. So, effective depth means from top of the beam to center of the tension reinforcement, that particular depth is known as 450 mm. And area of steel in the tension zone, here we are given 4 numbers of 20 mm diameter, and the effective span of the beam is 6 meters. In this case, the M15 grade concrete is used and Fe415 steel is used. So in this problem we have to calculate the uniformly distributed load, including its self weight, how much the beam will carry. So first of all, we have to calculate the actual neutral axis by equating the moment of compression area about neutral axis to the moment of tension area about neutral axis. That is, BNA squared by 2 is equal to M into AST into T minus NA. In this case, B is known, M is modular ratio, AST means area of steel in the tension zone, and D is the effective depth, NA is the actual neutral axis. So here we have to find out the actual neutral axis. All the values are given. AST is equal to 1256 mm square. Substituting all the values in the above equation, we will get NA is equal to 208.8 mm. Critical neutral axis, NC is equal to KD. K is equal to M sigma CBC by M sigma CBC plus sigma ST. Substituting the values, we will get K is equal to 0.28. So critical neutral axis NC is equal to K into D, that is 0.28 into 450, which will give 126 mm. So in this case, NA is greater than NC, so the section is over reinforced. So for over reinforced section, the moment of resistance will be depending on the concrete. So BNA into sigma CBC by 2 into D minus NA by 3. By substituting the B value, actual neutral axis value, and sigma CBC values in the above equation, we will get the moment of resistance, that is 4694.2200 Newton mm. In this case, we will get the value in Newton mm. So we have to find out the uniformly distributed load, how much the beam will carry. So for the maximum bending moment, the M formula is WL square by 8. As this is the UDL, we have to use this formula. If this is a concentrated load, we should use WL by 4. By substituting the L value, that is 6 meters, we will get, that is the W value of 11032 Newton per meter inclusive of self weight. If we want to find out the value which should be exclusive of self weight, we have to subtract the self weight of the beam by calculating breadth into width into unit weight of concrete. We will get the total load that can carry exclusive its self weight. Let's go for another example. A RCC beam width 300 mm and overall depth 500 mm. Effective span is 6 meters and the live load is 4 kN per meter. Find the area of tension reinforcement by using M15 grade concrete and Fe415 steel, and the modular ratio is also given in the problem, and the effective cover is 50 mm. So the self weight of the beam, first of all we have to calculate the self weight of the beam, that is 0.3 into 0.5, that is width into total depth into unit weight of concrete is 25. So finally we will get 3.75 kilonewton per meter, and the live load is already given in the problem, that is 4 kilonewton per meter. So total load is equal to self weight plus live load, that is 3.75 plus 4, 7.75 kilonewton per meter, and the maximum bending moment is WL square by 8, that is 34.875 kilonewton meter, and the effective depth is equal to 500 minus 50, that is 450 mm. Next, K is equal to m sigma CBC by m sigma CBC plus sigma ST. By substituting all the values, we will get K is equal to 0.28 and the modular ratio m is equal to 18, which is already given in the problem. So substitute all the values in the discharge form. Q formula, that is bending moment coefficient, that is Q is equal to half into sigma CBC into K into J. In this case, the sigma CBC value depends on the grade of the concrete, which is already given in the AS456. Just substitute all the values and calculate the bending moment coefficient, that is 0.635. By substituting all the values, we will get the bending moment for a balanced section. In this case, the maximum bending moment is 34.875 and the bending moment for a balanced section is 38. So actual bending moment is less than the balanced section. So the section is under reinforced section. By using the formula, that is BNA square by 2 is equal to M into AST into D minus NA. By substituting all the values, that is B, but we don't know NA, and substitute the modular ratio and D values, we will get AST is equal to 150 by 18 into N square by 450 minus N. And in this case, the section is under reinforced, so the moment of resistance of steel is depending on steel components, that is sigma ST into AST into D minus NA by 3. By using the trial and error method, we have to calculate the actual neutral axis, that is NA is equal to 121 mm. By substituting the NA in the AST equation, we will get the AST value, that is AST is equal to 370.88 mm square. By assuming the diameter of the bar for that particular beam section, we will get number of bars. Let's go for another problem, that is example 3. So in this case, we have to design the singly reinforced beam to carry a superimposed load of 6000 Newton per meter over a span of 6 meters using M15 grade concrete and Fe415 steel. First of all, we have to calculate the design constants, that is modular ratio m is equal to 280 by 3 sigma CBC. So in this case, M15 grade concrete is used, so we have to use the sigma CBC value of M15 grade and substitute the values. We will get modular ratio m is equal to 18.7. Then find out the K value. K is equal to m sigma CBC by sigma ST. In this case, we have to substitute the m value and sigma CBC value and sigma ST value. We will get K is equal to 0.289 and J is equal to 1 minus K by 3, that is 0.904. Then Q is equal to half into sigma CBC into K into J. This is the bending moment coefficient, that is Q is equal to 0.653. In this problem, the cross-sectional dimensions are not given. So first of all, we have to assume the overall depth of the beam by taking the formula, that is 1 by 10 of the span, that is 1 by 10 into 6000. So we have to assume the overall depth is equal to 600 mm. By assuming the effective cover for beam, that is 40 mm, the effective depth is equal to 600 minus 40. So we will get 560 mm. By assuming b is equal to small d by 2, that is 560 by 2, 280 mm we will get. Then calculate the self weight of the beam. Self weight of the beam is equal to, that is overall depth zero point 0.6 into width, that is 0.28, into unit weight of concrete, that is 25. We will get 4.2 kilonewton per meter. The superimposed load is already given in the problem, that is 6 kilonewton per meter. The total load is equal to self weight plus superimposed load. We will get 10.2 kilonewton per meter. Then calculate the effective span, that is effective span is equal to clear span plus effective depth, that is clear span is 6 meters, which is already given in the problem, and the effective depth is 0.56 meters, so we will get 6.56 meters. In this case the supports is not given, that's why we are considering this only one equation. If the support thickness is given, we have to calculate another one also, that is center to center of supports. So in this case that is not given, so we are considering the same one. So in this particular beam, the effect clear span is 6 meters and the support thickness is not given, and the uniformly distributed load is on the top of the beam. So the maximum bending moment formula for a simply supported beam with uniformly distributed load is WL square by 8. By substituting the W value and effective length value, we will get the maximum bending moment, that is 54.87 kilonewton meter. And by using the equation M is equal to QBD square, that is for balanced section, we have to calculate the depth value, that is D is equal to square root of M by QB. By substituting the M value, Q value and B value, we will get the effective depth, that is D is equal to 548 mm. As we already assumed that the effective depth is 560 mm, so our assumed value is higher than the balanced depth, so it is safe. Then calculate the area of steel in the tension zone, that is M by sigma st into J into D. By substituting the all values, that is moment, sigma st value, J value and D value, we will get the area of steel in the tension zone, that is 471.22 mm square. Here we are assuming the 16 mm diameter steel bars and the number of bars is equal to 2.34. So finally we have to provide three numbers of 16 mm diameter steel bars as tension reinforcement. So this is the final section we designed, that is B is equal to 280 mm and overall depth of 600 mm and effective depth of 560 mm. Here we got three numbers of 16 mm diameter, and here we are using two numbers of anchor bars with a minimum diameter of 10 mm